Hello guys, in this video we are going to talk about matrices. The idea is to define what is a matrix. We are going to start from the scratch and understand its basic properties. We will try to classify the matrices into different types that you will see that are important during this week. Which are the requirements? Very low. Compared with integrals or derivatives, we only need some basic operations with real numbers. Okay, so let's start with matrices. So the idea, we are going to introduce the matrix using a linear system, okay, linear system of equations. As you can see on the screen, we have a linear system. The idea is that this linear system can be written in a matrix form. And how are we going to do that? We are going to just take the coefficients of the variables, the unknowns. As you can see, we have three unknowns, x, y, and z, and I'm taking the coefficients of each of them, okay? Same order, by the way. It doesn't matter if you just rearrange x, y, and z, but please be consistent with the matrix, okay? This column belongs to x, y, and z. And this column, the independent terms, is the one that it's on the other part of the equality, okay? So we are just using the matrix form of a linear system. It doesn't matter if the matrix does not come from a linear system. We can introduce matrices in general. In this case, I'm just taking a linear system from the beginning just in order to help you remember that this can be done, okay? But I could just have started with this matrix directly, okay? Okay, each row of this matrix represents an equation. Each column, it's one of the variables. These numbers are the coefficients of the x variable, y variable, and z variable. Okay, in general, what I was talking about, do I need a linear system to introduce a matrix? No. A matrix of order m times n, it's numbers arranged in columns and rows, as you can see here. These A11, A12, A1n are just numbers. The subindexes 1, refers to the row and column. Always in this order. The first number is the row, okay? And the second number, it's the column in which this number is, okay? Normally, we denote this like Aij. Okay, it's A is the number and AJ is the position in these arranged numbers, in arranged rows and columns of numbers. Okay, so the idea is that this is a matrix. Let's see some examples. This is a matrix with 3 rows, 4 columns. This is a matrix with 3 rows, 3 columns. This is a matrix with just 1 row, 3 columns, okay? Be careful with that. Each of them will have a type and a specific name, okay? We will see in 1 second. Okay, more things. 2 matrices, we say that are equal when they are the same term by term. The first number in the first position is equal to the first number in the first position on the second matrix. Okay, we need to compare term by term. And then if everything is the same, then we say that the matrices are equal. What do we call a row matrix or row vector? Is when we have matrices of the order 1 by n. Okay, 1 row, n columns. As I told you before, this 1, 9, negative 2 is just 1 row, 3 columns, okay? When do we say we have a column matrix or column vector? Is when I have different rows but just 1 column, like in this case. I have 3 rows but just 1 column. The null matrix is the matrix whose all of the elements are zeros. In this case, okay, be careful, because in this case I have the matrices with 2 rows, 3 columns, but null matrix could be of any shape. The key point is that all the elements are 0, okay? Don't think that the null matrix has this dimension exactly, okay? It's just an example. The key point of a null matrix is that all the elements are 0. Okay, more things. The transpose of a matrix, that is important. How do we calculate the transpose of a matrix? The idea is that, let me say it just very short, in a very short way. We just change rows by columns. Let me see. I think I have an example here. No, okay, I'm going to show you here. The idea is, in this matrix is 3 rows, 4 columns. Then the transpose of this matrix is 4 rows, 3 columns. And how do we build this transpose matrix? The idea is to take, for example, the first row, 2, 3, 5, 7, and you need to write it as 2, 3, 5, 7 in a column, okay? The first row becomes the first column. The second row, 0, 1, negative 3, 2, becomes the second column. The third row becomes the third column, okay? So it's just like flipping a little bit, 90 degrees, this matrix, okay? So rows becomes columns, or if you want, in a different way, you can say that columns becomes rows, okay? But it doesn't matter. The key point is that you just need to flip these elements. The opposite matrix is the matrix multiplied by -1. It's the matrix such that all the elements has the opposite sign. For example, 2, 3, 5, 7, 0, 1, -3, 2, 4, 5, 7, -1. The opposite matrix is the one that all the elements are the same, but with different sign. Okay, if I have 2, then it's -2. If I have 3, this is -3, 5, -5, and go on, and so on. Okay, this opposite matrix is used when we are adding matrices, okay, to obtain the null matrix. But okay, it's just in the real space, it would be like if I give you a 3, you return -3, or if I give you 5, -5. Okay, that's the same idea. Okay, a square matrix. When do we say a matrix is a square? Okay, when we have the same number of rows and columns, like in the example. As you can see, I have 3 rows, 3 columns. It's a square matrix, okay? Piece of cake. What is the main diagonal of a square matrix? Okay, the main diagonal are these elements. I'm so sorry, let me go back 1 second. They are in red now. It's -2, -3, -1. The one in these positions. If I want to be more specific, it would be the elements 1, 1, 2, 2, 3, 3, okay? These elements, this is the main diagonal. What is the secondary diagonal? Just the opposite one, that one, okay? It's 7, -3, 5 in this case, okay? Main diagonal, the opposite, the secondary diagonal, okay? Piece of cake, I think so. Okay, what is a diagonal and identity matrix? A diagonal matrix is the one that has zeros, all the elements outside of the main diagonal. Look at this. This is the main diagonal, -2, 5, -1, and the rest of the elements are all zeros. Does this mean that I cannot have zeros in the main diagonal? No, of course. The key point of the definition is I have some elements in the main diagonal and the rest are all 0. It doesn't matter if this 5 is also a 0. The key point is that these 3 elements above the main diagonal are 0 and these 3 elements below the main diagonal are zeros. And a specific case, and a very specific type, when the elements of the main diagonal are all 1s, this is called identity matrix, okay? And this matrix is the equivalent of the 1 in the real space when we are multiplying numbers. 5 times 1 is 5. 2 times 1 is 2, okay? So, in these cases, the identity matrix is like the 1. Any matrix multiplied by the identity matrix is exactly the same matrix, okay? And it's a very important matrix. Keynote, be careful. Identity matrix should be always a square. I mean, the same number of rows and columns. It's completely different from the null matrix when it was all zeros, but it can have any shape, okay? In this case, the identity matrices should be a square. It doesn't matter if it is order 3, like the one you see on the screen, or even greater or smaller, okay? Okay, when do we say a matrix is symmetric? Okay, we say that it's symmetric when the elements above and below the main diagonal are the same. In a mathematical form, we say that Aij equals Aji. For example, look at these examples. I have -2, 5, and -1 on the main diagonal. But these elements, they are. I don't care if I'm going to check if the matrix is symmetric or not. The idea is that, look at this. The element 1, 2 should be equal to the element 2, 1. The element 1, 3, this number 1, should be equal to the number 3, 1, in the position 3, 1. This element in the position 2, 3 should be equal to the element in the position 3, 2. It's like if you fold, you got the main diagonal, if you fold the matrix by the half along the main diagonal, the elements are the same. Okay, look at this, 3, 3, 1, 1, 0, 0. Okay, the elements in the main diagonal, they don't care just to identify the matrix as a symmetric matrix or not. Be careful, when do we say a matrix is antisymmetric? Okay, look at this example. The condition is that I in the position A and the position Ij should be equal to the negative in number in the position Ji. Yeah, it seems strange. Come on, let's see an example. Look, the number in position 1, 2, -2, should be equal to the element in the position 2, 1, but with different sign. If I have here -2, this should be 2. If I have here a 4, then this is -4. If I have here -5, then this should be 5. It's like the one it's like the symmetric matrix, but changing the sign. And also, very important, if this condition must be hold, the elements in the main diagonal should be 0, because 0 is the only element that is exactly the same as -0. Okay, the other elements does not verify this condition. So an antisymmetric matrix should have zeros in the main diagonal, and the elements above the main diagonal and the numbers below the main diagonal are the same, but with different sign. Okay, guys, what have we seen? We have reviewed very fast the definition of matrices, and we just define or use different types of matrices that I'm completely sure will be helpful for you. Okay, guys, thank you for your attention.